All right, so in our video series, we've already talked about extreme value theorem, which required just that your function was continuous on an interval. And this video is going to be about Rolle's theorem and mean value theorem. So Rolle's theorem and mean value theorem require one more piece or one more condition in order to be applied. And what you have to know is you have to know that the function is differentiable on that interval. Okay, so if you end up having a cusp point, or if we're looking at absolute value function, or we're looking at maybe like the cube root function, Rolle's theorem is not going to apply because that's not a differentiable function on the interval probably that we're looking at. Okay, so Rolle's theorem says that if you have a continuous differentiable function on a to b, notice right here, okay, before I jump into the other condition, but a continuous on the closed, differentiable on the open, from A to B. And we also have this unique condition, okay, that f of A equals f of B. Notice on all of these, the outputs of my endpoints are equal to each other. The outputs of the endpoints are equal to each other. Then there exists at least one time on that interval where you will have a horizontal tangent line. There exists at least one time where you will have a horizontal tangent line. Well, that's because in order to get from this point to this point, either it's constant all the way across, or you have to like go up and down, or if you go down, you have to come back up. Or notice here we actually have two. Now the theorem only guarantees one to happen, but it could happen multiple times. Think about like the sine and cosine graph, right? If we look from 0 to 4 pi on the sine graph, now one of these is only guaranteed, but on this graph we actually have 4 times that this happens. So again, I'm going to review the conditions. Still continuity, super important, okay? Differentiability, additional condition. For Rolle's theorem, your outputs on your endpoints have to be equal. If that's the case, then you have to have at least one horizontal tangent on that interval, okay, specifically on that interval. So let's go ahead and look. I have x squared plus 2x. It's a polynomial, so polynomials are going to be continuous and differentiable. So then the next thing we need to check is for a equals -2 and b equals 0, are those function values equal to each other? That's the big condition here. So let's go ahead and find that and make sure. Okay, so f of -2 is -2 squared plus 2 times -2. That gives me 4 minus 4, which is 0. F of 0, well, when I plug in 0 to both of those, I get 0. Now let's think about what we know about quadratics. This is a quadratic function that opens up, and I now know where my 2 zeros are. Well, the vertex has to happen between those 2 zeros. And if we use vertex form, whatever, we know that that actually even occurs at x equals -1. But what this theorem says is because f of b and f of a are the same output, I must have one point, ooh, that was a terrible graph, one point between them where I have a horizontal tangent line. All right, let's look at our second example right here. So f of x is x cubed minus 4x. Again, it's a polynomial, so we're continuous and differentiable. F of -2 is -2 cubed minus 4 times negative 2. I end up getting 8 here, negative 8 plus 8, so I end up getting 0. And f of 2 is 2 cubed minus 4 times 2, also 0. So because these outputs are the same value, and let's think about this function. So if I factor out an x, I get x squared minus 4. So that cubic function will have zeros at plus or minus 2, which we know because we just found them. Okay. And 0. And then it's a cubic function. So right here. So it makes sense. Now I'm only guaranteed 1, right? Oops, that looks like a 2, sorry. I'm only guaranteed 1 between these 2 points. And it just so happens I get 2, right? But there we go. Now, on both of these examples from the text, they included the zeros, which is nice, but I don't want us to think that like your outputs have to be 0 for there to be a 0. So I want to look back here at A, and I want us to look at from negative 3 to 1, okay? So f of negative 3 f of negative 3 is negative 3 squared plus 2 times negative 3. So I end up getting 9 minus 6, I get 3. And f of 1 gives me 1 plus 2, I get 3. So because these two outputs are the same, up here, okay, it must be true that a maximum or a minimum, okay, local max or local min, must occur between those two values, okay, between negative 3 and 1 here. Now, an extension of Rolle's theorem is mean value theorem. Mean value theorem, when you think of like average and mean the same thing. F of A and F of B don't have to be the same, okay? F of A and F of B don't have to be the same. Well, there's no longer a guarantee that there's an absolute max or absolute min, okay? Because the reason that there's an absolute max or absolute min is because those values, okay, like, how do I explain this well? The values were the same, so they're like, it had to go up and back down, okay? But in the mean value theorem, it says that if you look at the slope of the secant line between A and B, that there must be a tangent line slope parallel, or tangent line parallel to that secant line, so the slopes must be the same. So again, continuous and differentiable. There must be one point on that interval where the slope of the secant line between A and B is equal to the slope of the tangent line somewhere on that interval. All right, so let's look at the square root function. Let's just go ahead and draw it from 0 to 9. Okay, so 0 to 9. Now, if you are like, but the square root function is not differentiable at 0, remember we need to be continuous on the closed, which is true, and differentiable on the open. So it's actually okay if we're not differentiable at the endpoints. Now let's draw this visually, and then we'll also do it algebraically, okay? So what it means is the slope of the secant line between the two endpoints, there must be a point between 0 and 9 where the slope of the tangent line is the same. So let's see how we look at this. M tan. Okay, we're going to try to figure out where that is. Find these values of C guaranteed. So let's find f of 9 minus f of 0 over 9 minus 0 first. So that's going to be the square root of 9 minus the square root of 0 over 9, 3 over 9, or 1/3. All right, I also need to find f prime, just generically, 1 over 2 root x. And then I say that there must be an f prime of c, so 1 over 2 square root of c, that is equal to the slope of the secant line. Because the numerators are both 1, if I cross multiply this, I end up getting that the denominators have to be equal to each other. If I divide by 2 and then square both sides, I get that c must be 9/4. And so at 9/4, at 2 and 1/4, wherever that is, if this is 4.5, I don't know, somewhere in here. Well, that makes sense, right? 2 and 1/4, that slope of the tangent line will be the same as the slope of the secant line between the two endpoints. And that is mean value theorem. Now, Rolle's theorem kind of says the same thing. It's just the secant line slope is 0. So that's why you end up having a tangent line of 0. So mean value theorem takes it kind of one step further and says, like, if you have two endpoints and a curve, then there must be one point somewhere between those two endpoints where the tangent line slope is equal to that secant line slope.